Alrighty, so we are in time. Let's start. So this is the periodic table you already picked up from the laboratory, I guess. I'm going to use this one. And sometime I also go to the website and show you from there. Yeah, so this is very important tool and we are going to use this one. Yesterday I saw you some blue color and some orange color in this periodic table. So I'm going to show you this here today. So this is the periodic table. And in the periodic table, you see like this. So we have a table like this one, and like this. And 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, like this. So something like this, and you see 2 rows here. So this is called the periodic table. So what kind of all the material are in the universe people have found? They have put every element here in this periodic table. There is nothing in other place if you don't find it here. So everything that we found in nature, all those elements are here. Yeah. So this guy is called group 1. This is called group 2, and this is called group 3. This is called group 4, group 5, group 6, group 7, and group 8. So we have group 1 to group 8 like this. Yeah. And so these 2 groups, so group 1 and group 2, these elements are called S block. So there is a reason why they called S block. It's just like the we are in the Phillips Hall block, right? Just like the house. So these 2 groups are called S block. And this group 3, group 4, group 5, 6, 7, 8. These are called P block here, P block. And the middle element here. So there are a lot of elements here. So these are called D block, and the 2 rows here down here are called the F block. So S block elements show similar properties, right? For example, we are in the Phillips Hall here. So most of the students here take the science courses, right? Just like that. So the S block. And these D block elements have very similar properties, but they are a little bit different from here, a little bit different from here, but all these elements have very similar property. That's why we how we classify the materials. Make sense? And then most of these elements have very similar properties. And when you see upper level somewhere here, they have one kind of property, and when we go down, there are other kind of the properties. So, and these elements have very similar properties. Yeah. So grouping means the dividing all elements in different group means they have very similar properties. So if you see in periodic table, you might see hydrogen here and lithium here and sodium here. So if you study hydrogen, lithium, sodium, and these elements, they would show very, very similar characteristics in the chemical reaction. Yeah, although they look different physically, but they show very, very similar characteristics when we do the chemical reaction. Make sense? And when you go here and you will see beryllium, magnesium, calcium, this kind of, so all these elements behave very the same way. They make the similar kind of compounds. Yeah. So what I wanted to stress here is not talk more about the chemical property here. So, so sometimes these elements, the group 1 elements are called alkali metals, and so these grouped elements are called alkaline earth metals, So that's how they named a long time ago. Alkali metals mean like the basic. So they are not like acidic, they are like basics. Yeah, they behave like the base. The elements behave like the base. And this element, this D block element, they call transition element. Transition elements. So since they are between S block and P block, so it's kind of the transition, right? Like the transition from high school to college, something like the in between elements. Make sense? And these elements are called P block elements. And this group 8 element here, the last group element are called inert element, INERT, inert element, meaning that these elements here, they don't react in chemical reaction. So they are there and they just sit there and they don't interact with other elements or within themselves. So they are called inert elements. Make sense? So, and I told you yesterday, so there are in that periodic table here. So all those blue elements you see here. So I just make a small line here. So these elements here and this hydrogen, these are non-metal, and all those blues here are metal, and there are some green, so boron, silicon, germanium. There are some elements, they are metalloids. Yeah. So in exam, what would you see is like this. So I will give like 5 or 6 elements from here, and I would tell which is an element and which is not which is a metal and which is not a metal. Yeah. Something like that, or which is a metalloid. So I might pick some element from here and say which one is metalloid. So you just look at the periodic table and identify which one is a metal, which one is non-metal, which one is a metallite, or something like that. Everybody got that? So, and although it is a hydrogen is a S block here, this is non-metal. It does the similarity in chemical reaction like lithium and sodium, but most of the hydrogen properties are non-metallic properties. So only one element here is non-metal, and other are here, somewhere here are non-metals. Yeah. So if you see all these elements here, there are I think 118 or 115 elements people have found so far, and about 18 elements are non-metal. So out of all elements of the periodic table of the universe, right? So about 18 elements are non-metal. About 6 are metalloid. So 6 are metalloids. So metalloids, and about 91 are metals. So there are too many metals in the too many elements. They are metals, but we have very small number of the non-metal. When we go outside and look around, we see everything is a non-metal, right? Like the wood is a non-metal, plastic is non-metal, water is non-metal, everything is non-metal, right? But those all non-metal are made up of very few elements from here and this hydrogen. So about only 18 elements are non-metal, and they make most of the material that we see around, right? Like silicon, silica, the river, lakes, snow, ocean, whatever, all are non-metals. Make sense? So there are few non-metals, and they make most of the material of the universe. Everybody got that? So like this. Now we call these boxes elements. So, so this is hydrogen. We call hydrogen element. This is lithium element, sodium element. So, what is you see in this periodic table? They are called elements. Something you don't see in this periodic table are not the elements. Make sense? In chemistry, we define the elements that way. Everybody got that? So anything you see in the periodic table is an element, and something that you don't see here is not the element. Yeah. So for example, I might give you a question like, okay, is a iron and iron, this is the iron, is this an element or not an element? Yeah, so you go here and look the periodic table. Okay, so it's in the periodic table, so this is the element. Make sense? So somehow if you combine two elements together, so let's say this is the iron and here we have somewhere is a oxygen here. So if I combine that guy with this guy in certain ratio, then I have two elements combined here with certain principle, certain rule, that's now become the compound. Make sense? So if two or more elements combine chemically, they give a substance that is called compound. So FeO is not an element. Fe is element, O is element, but FeO is not an element. That's a compound. Make sense? So you might see some question like, okay, I have a FeO, H2O, or H2, or something like, which one is an element? So look here. So here, iron and oxygen are combining each other. So this cannot be element because FeO is not in periodic table. Make sense? So FeO is not element. Water, here is hydrogen, here is oxygen. So they are combining there. So this is also not element. This is a compound, right? But hydrogen, you can see here somewhere hydrogen is here. So two hydrogen are combining here and giving a molecule like this, and that's an element. This one H you can easily see, and H is combining with another H, not with other element. Make sense? So H2 is the element. Everybody got that? So S2 is the element. Is O2 element? Yes, O2 is also element because this is one O, this is another. So there are two O's, so O2 is also element. Make sense? Everybody got that? So like this. So if you see two things sitting together, that is a compound. If you see only one kind of material sitting together, that's a element. So for example, you might see H2, so two H are sitting together here. You may see chlorine Cl2, so two chlorine are sitting together here. So you may see flow F2 like this. So this is element, this is element, this is element, right? But if you see H and Cl sitting together, now this is not the element, that's a compound. Make sense? So like this. Good. So this is very important. So if you know how to read this guy, most of the chemistry is all here. Yeah. So, but we need to know how to read this chart. Now, let's go here. Now, I'm going to define one mole here. So, mole is very important in chemistry. Just like in everyday life, you go to a store and you buy, okay, give me 1 pound of bread, right? So it's a mass, right? So it's a kind of the unit. So in chemistry, we use mole. In everyday life, we use pound, but in chemistry, we use mole. Yeah. So we need to know what is mole. So mole. So I'm going to mole mean basically is an English word, and that says moles mean very small amount. So mole literally translate into the very small amount, small thing, right? So let's say look the periodic table here, and then you will see the number here. So there is there are two numbers. One is a big number, and then there is another small number. So look the big number here. Big number is the mass of that number. Yeah. So we'll talk about where they come from. So I'm going to look one here. So beryllium. So I pick one element from beryllium here from group 2. So this is group 1, group 2. So I pick the beryllium here, and you will see two number there, and one is 4 here, and another is 9.012 here. So so this is not the mass. So small number is not the mass of the beryllium. So I don't look the small number. I look the bigger number for mole. Yeah. So 9 is the, so beryllium has the mass of 9. So 9 what? 9 is a kind of unit. Yeah. We'll talk what that unit is. So what is the mass of the beryllium? So we call, oh, okay, mass of the beryllium is 9 unit, like 9 kilogram, 9 milligram, 9 centigram. But here we call 9 atomic mass unit. Atomic mass unit. So we'll talk what is what this one. So atomic mass unit is like the gram, centimeter, meter, feet, whatever we talk, just like that, right? So 9. So if you say I have 1 mole beryllium, 1 mole beryllium, that means you have 9 gram beryllium. Everybody got that? So whatever the number is there, if go to the go to the laboratory. So there is a lot of beryllium here in this bottle, and you have a balance. Take beryllium from here and put in this balance until you see 9 gram here. So when you see 9 gram beryllium you put, that means you take 1 mole of the beryllium. Everybody got that? So basically it works like that way. Now, so this do some other examples. So how about the water? So water. So now we need to calculate the mass of this water molecule, right? Now, how many hydrogen are there? So I have 1 hydrogen here. H2 means I have 2 hydrogen here, right? So I have 1 hydrogen, and this 2 means I have 2 hydrogen here. I have another hydrogen, and now I have 1 oxygen here. Everybody got that? Now I go to the periodic table here, and hydrogen is 1.008, the bigger number. There are 2 numbers. One at head is 1, and at the foot there is 1.008. So I take that bigger number. Make sense? So bigger number is the mass of that hydrogen. So although it's 1.008, so I just round it and I write 1. 1.008 is close to 1, right? So I just write 1. Make sense? So look here, if you write around 1.008, it's very close to 1. So I just drop these numbers and I just write this 1 here. Yeah. Now some professor says, oh, you need to write all 1.008, but in laboratory it's impossible to work with 1.0 that 0.008. So if you could measure about 1 around 1, that's good. Yeah. So you really don't need to worry about this very, very small number behind. And this hydrogen is also 1. Now let's look oxygen here. So oxygen here is the bigger number is 15.99. So if you look there, it's oxygen 15.99, 15.999. So you can see 15.999 here like this. So that 15.999 is a little bit hard to use again, right? So I round it to 16. It's about 16, right? 15.99 is 16. Make sense? So I write that as 16 here. So if I start to write very big, small number, I just totally lost the track because I'm now struggling with remembering very, very those small number rather than learning chemistry, right? So we just try to round and use the easier number. Make sense? So like that. So that's the oxygen is 16 here. So 16. So now I add all these numbers, 16, 17, 18, right? So this is 18 gram. Make sense? So now you take the water and go to the balance and put your beaker here, make 0 and add 18 gram water here from somewhere, and this will show the 18 gram. The balance shows 18 grams. So if you have 18 gram water, that is 1 mole of water. Make sense? So how to find the mole? So first of all, you need to know this. What's the molecular formula? Then you need to know how much is the mass of H, how much is the mass another H, and how much is the mass of O, and you add all. So whatever the number comes here, so that number you need to measure in gram, not kilogram, not pound. It's in the gram. Make sense? So that gram is very important. Why gram? Why gram? Why not pound? Why not kilogram? Because people have defined this chemistry that way. Whoever did this chemistry very first time, long time ago. Everybody got that? So because they defined and they started to do that way, so everybody followed them and let's do that way. Yeah. So if somebody has done another way, we could do another way too. Yeah. But all chemistry book, everybody do this way, so we need to learn this way. Make sense? Good. So it's just how people develop at the beginning, and we just other people just followed what we do. Yeah. Good. So now, so I just talk about the water. Now let's talk about the. So this is very important. So mole, molarity. So all the time we will be doing this kind of thing. Now I have another example here. So hydrogen. So what is the 1 mole of hydrogen? What is the mass? 1 mole of hydrogen. So again, look the periodic table, find hydrogen. There are 2 hydrogens. So I have 1 hydrogen, another hydrogen. So 1.00 something, that means 1. Another is also 1. So I have 2, right? So if you go to the laboratory and measure 2 gram of hydrogen, that means you measure 1 mole of hydrogen gas. Everybody got that? So those things are written here. How about 1 mole of carbon dioxide? So 1 mole of carbon dioxide. So now again, go to the periodic table here. Carbon is here is 12. So you can see the bigger number with the carbon is 12. So this carbon is 12. Oxygen is, I already told you, that's 16, right? One oxygen is 16. I have 2 oxygen there. So 1 oxygen, another oxygen, right? So 2 oxygen. Now I just add those and I get 44, number 44 here. So I go to the laboratory, find the bottle of the carbon dioxide and put 44 grams of carbon dioxide in balance. And that means that I measure 1 mole of carbon dioxide. Everybody got that? Easy, right? So 44 gram of gram, not 44 pound, not 44 kilogram, not 44 milligram. It's always gram. Yeah, good. 44 gram of carbon dioxide is 1 mole of carbon dioxide. Now let's look 2 example here. How about oxygen? Same thing. So oxygen is 16. So 15.999 means 16, right? I have 2 oxygen there, 16 and 16, 32 gram. So 32 gram of oxygen, meaning that I measured the 1 mole of oxygen gas. Everybody got that? Good. Now, how about 1 mole of oxygen? Again, that's 32 gram. How about nitrogen? So let's talk about the 1 mole of nitrogen. So look the N here. So N, 1 N here is 14.007. So N is 1 N is 14 point. So N is 14.007. Again, it's very hard to work with this small number. So I just round it. 14.007 is close to 40, right? So 00 is really small, right? So I just round that number there and I have 2 N there. So 14. Now I have 28. So if I measure 28 gram of nitrogen in balance, I measure 1 mole of nitrogen. Everybody got that? Now some of these elements exist as N2, H2, O2, F2, Cl2, like this. But many of the elements, so some of these elements which are non-metal, they exist like this. But most of the metals, like the group 1, group 2, or these D block elements, they exist as just only one. So, for example, this group 1 element, hydrogen, this hydrogen exists as H2. But if you go a little bit down that metal, Li, that exists as Li, not Li2. So we'll study that in future. Yeah. So if we talk about the 1 mole of lithium, we are not looking Li2 because Li never exists as Li2 in nature. So if you go and find the lithium in nature, you always find only one lithium sitting alone, not with like combining like N2, H2, O2. It just sits like Li. Everybody got that? So what is the 1 mole of lithium mass? So lithium. So I'm going to look here. Lithium is 6.941. So this is lithium mass is 6.941. Sometimes you can just do 6.9. You could probably you can use 6.9 like that. So it's okay 6.9. Yeah, it's not hard to remember. But if it were something like 6.002, I would just use 6. Make sense? So 6.9, a little bit harder to round to 7, right? But if it were 6.99, probably I could write 7.2. Make sense? But when you do the calculation, that point really doesn't make that difference. So while you study the general chemistry or you don't go to work in the laboratory, you might think, okay, should I use 6.9 or 6.94 or 6.941941 or maybe 6.8 or something like this. So either you measure 6.9 or 6.94 or 6.945 or 6.8. At the end, you are doing some kind of the calculation, and this is almost, they all give almost the similar answer because we are not looking at the absolute number. We are just making some comparison. Okay, from how much we produce, right? So so this number very close to each other. So now what else I have here? Now Now, classification of the matter. So I am in the fourth slide, classification of matter. So classification of matter. So what is matter? So matter is anything that has a mass and that occupies space. So basically anything you see around here or you don't see, like the air, nitrogen, hydrogen, we can't see, right, with our eyes, right? So anything that has mass, we can measure and that occupies the space, that is called matter, right? So matter is like the air, water, whatever. So air, water, carbon dioxide gas. So carbon dioxide. So I write, so three kind of matter here. So air also occupies the space. Air has also mass, right? So air is a matter, or carbon dioxide. This is a gas and it also occupies space. It has a mass, and water is a liquid. And let's write some solid here. So iron. So I'm going to write these three things here. So basically, in our everyday life, we only see three kinds of matter. There are no more than three state of matter. So there are another state of matter they call the plasma. So they say that this kind of the matter is state in somewhere in the star or very high temperature condition, sun there. So but in Earth, we don't see plasma condition that often. Yeah. So if you hit some gas to very, very high temperature, they become like neither gas nor fluid, nor liquid. So they occupy another state there. That's called the plasma. Yeah. But we don't study plasma here. So water is a liquid. So this is a liquid state, and carbon dioxide is a gaseous state, and iron is a solid state. So all matter we see or we feel in everyday life are of exist in three states. So liquid, gas, and solid, or solid, liquid, and gas. Everybody got that? And what's the fourth state of matter? Although we don't see it here, fourth state of matter is called plasma, and we don't see it in Earth that often. Yeah. So like that, and so this is the physical state. We are classifying the material according to the physical state. The physical state. How do we feel? Physical state means how do we see and how do we feel, right? Physical state. And classify according to composition. So this is according to physical state. How do they look like? Now, you can also classify the material according to composition. So composition meaning that element. So elemental form, then compound form, and mixture form. MIXTURE, mixture form. So we can also classify material in terms of the composition. So what is element? So element means whatever you see in the periodic table, that's the element. Make sense? We already talked about it, right? So how about so like let's say lithium. So lithium, you can find this material in the periodic table. So it's an element, right? And what's a compound? Compound is when two elements combine together in certain ratio, then that combination is called compound. Make sense? So for example, if I react lithium with oxygen, so I make a compound like this, Li2O. So Li is one element, oxygen is another element. So two lithium are combining with one oxygen here. So this kind of existence is called compound. Make sense? When two elements combine with each other in certain ratio. If you look at the ratio here, what is the ratio of lithium and oxygen? Lithium is 2, oxygen is 1. So 2:1, right? So in compound, element combine in certain ratio. Make sense? So Li, if you try to make the Li to react the lithium with oxygen, they always combine like that way. So always 2:1. So 1 oxygen hold 2 lithium. There is no other way. Everybody got that? So that's a compound. And how about the mixture? Now I take some lithium and then I take some sodium and I just throw in the bottle. So I can put 50 atoms of lithium and 60 atoms of sodium together, or I can put 100 atoms with 1,000 atoms of sodium. So I can mix anything in any ratio. So that kind of existence for the mixture. Make sense? So we don't have to be in the definite ratio. Yeah? Everybody got that? So for mixer, we are just taking material from different places and dumping whatever we like. Yeah? But in compound, you cannot dump a lot of lithium and a lot of oxygen there. They always sit like Li2, 2 lithium and one oxygen sit together here. Make sense? Good? So like that. Now let's talk about some properties of the this material. So I'm now in the 5th slide. Now let's do a comparative study of solid, liquid. Maybe I start with solid, liquid, and gas. Liquid and gas. So we say in the physical, if we look there, existent with our eyes, or we touch them. So these are the physical characteristics of physical state of the material. So solid. So let's say if you may have a small, this is a beaker here. You have a small amount of ice here. Let's say 1, 2, 3, 4, 5, 6 molecules of water are sitting like that. So this is an ice piece, right? So ice piece. So that's a solid. Make sense? Now, so this is ice. Now heat it. So if you hit this ice, what happens is this water molecules. So water has a little bit anomalous property, so it may not make sense here, but it's okay. You will know that. So if you hit this one, so this molecule, so this they are sitting very close here. So in water, they start to go like this. So you got it. So the molecule, the water particle now move further. So this is solid, the particles. So they are made up of a water particle here. So one water particle, another water particle, another water. So 6 water particles are sitting there, and it's ice there. Make sense? So the intermolecular distance here is really, really small. Can you see this? But when they become the solid are melted and becomes liquid, look here how the particle move further from each other. Make sense? So the interparticle distance becomes very big here, right? So they are farther. So these are very, very sitting very closely to each other. So they are moving, but they are not really moving that fast. Make sense? But here, since there is a lot of room to move here, these particles are moving faster. Make sense? So there are 6 particles of water. There are also 6 particles of water here, right? But this is in the solid state. So they are pulling with force, certain kind of force with each other, and these particles are not moving fast. But here, the interparticle distance in the liquid particle is large, so they can be easy to move from one another. So you cannot separate ice particle easily, but you can easily separate this water molecule and pour in another beaker, right? So this is our lab number 2. So you will be doing some simulation in lab number 2. Make sense? So now heat this liquid. Still there are 6 particles. Now heat this particle further, and what happened is this. Look here. Now 1, 2, 3, 4, 5, 6. Still there are 6 particles, right? Now see how far these particles are. So this is the gaseous state or vapor state. So the particles are really far from each other, and they are rapidly moving. Make sense? So they have a lot of energy. So this is solid, this is solid, this is liquid, and this is vapor or gas. So you can easily see in solid, the particles of the material are closely or tightly bound to each other, and they are, although they are moving a little bit, they are vibrating, they are not free to move from one another far. Make sense? So for example, this table looks like the continuous continuity of the matter, but it's not the continuous state of matter. It's made up of the particle, and these particles are, although they are moving slightly, they are not, these particles are not allowed to flow from here to another place. So it's in the same state. But if it were a water table, the water particle would be sitting like this, and they would not be attracting each other with that high force, and it's easy to splash another way. Make sense? So like that. But here in the gas, still there we have a 6 molecule of water here, and they are in the gas state and they really occupy a high volume. They are moving very, very fast. The interparticle distance is very, very large, right? Everybody got that? Like this. So if you look here, so they call the thermal. So that these particles are vibrating. They are not like sitting there and do nothing. So they are also moving. So that movement we call as a thermal motion. Yeah. So thermal motion. So thermal the vibration. So thermal motion here is thermal energy is very low. Thermal energy very low. Very low. So these particles are moving, but not moving that fast. So thermal energy is low. Here, thermal energy is high. Thermal energy is high because these particles are moving faster. Make sense? Here, the particles are moving really, really fast, right? Because we hit them and the molecules are just jumping everywhere. Yeah. So the thermal energy here is very high. Thermal energy in gas is very, very high. Should I put this kind of problem in homework 1? So you will see in the homework 1. Yeah. So which state has a very large thermal energy? Yeah. So which are meaning that thermal energy means in which state the particles are moving too fast. If the particles are moving too fast, they have the more energy, right? So for example, if the car we are driving the car very, very fast, that car that car hits somebody, that can kill easily, right? Because the car has too much energy. But if the car is moving slowly, that has small amount of kinetic energy, and it pretty much cannot impact anybody. I mean, it may impact, but it cannot impact as effectively as a high-speed car, right? Make sense? Good. So thermal energy. Now, what I have here is a so shape. If you look the shape, so if you look the shape of the ice is like the solid is very nice. It looks like a cube, right? We call the ice cube, or you can make the moon shape ice or whatever shape you like, right? Because the solid has very definite shape, right? You can make whatever the shape you like. Make sense? But liquid don't have shape. If you put this in the cylinder, the cylindrical bottle, the liquid take the cylindrical form, right? It looks like a cylinder, right? If you put the water in the bottle is cylindrical, so the liquid looks like the cylinder, right? But if you put the same water in the plate, the water looks like the plate, right? So the liquid takes the form of the container. So how does the container looks like? That is the shape of the liquid. Yeah, everybody got that? So if you go to the river, the water looks like a river, right? If you go to the lake, the water looks like the lake, right? But just like that. Makes sense? So this has a definite shape. The shape of the solid is definite, always definite, like the cube, just like the rectangle, right? So something like that. There's a cylinder, right? So these are the solid and they have definite shape, but the liquid don't have definite shape. They take the shape of the container. If you put in the cylinder, it takes the shape of the cylinder. If you put in the plate, it takes the shape of the plate. And similarly, the vapor or the gas also don't have its definite shape. If you put in the cylinder, gas take the shape of the cylinder. If you put the gas in the balloon, it looks like the balloon, right? So it just takes the shape of the container. Make sense? So like that. And shape. So indefinite shape. How about the volume? So let's talk about the volume. So volume. So the solid has a definite volume. For example, this is a duster. How do you calculate the volume of this guy? You measure the length, you measure the breadth, and you measure the height, and you multiply length, breadth, height, and you get the volume, right? So solid has definite volume. Make sense? So solid has definite volume. Now, how about the liquid? Liquid also has a definite volume. For example, you go to the store and you buy 1 liter water, right? So 1 liter water or 2 liter water. So definitely you are buying a definite volume of water, right? But gas don't have a volume. So, I mean, they have volume, but their volume depends on the container. So let's say you have a 1 gram oxygen. So oxygen is used in the hospital for the patient, right? So they help in the breathing, right? So if you have 1 gram oxygen and you are putting in a small cylinder like that, let's say 1 liter cylinder, so that 1 gram oxygen occupying 1 liter volume. Make sense? But what you could do is you could take a small amount of even half liter cylinder here, and you put the 1 gram gas here and compress it with a certain applying certain compression mechanism, and you can put that 1 gram within half liter. Same amount of gas, but you are just compressing or allowing to expand, right? So gas doesn't have definite volume. So if you compress it, for example, if I take a small perfume bottle here, which is, let's say, very small like this here, perfume means is a gas. So it's confined within very small, maybe 100 milliliter bottle here, right? Now, if I just open the cap here, a little bit perfume will fill all our room, right? So it just depends on the, it doesn't, meaning that it doesn't have the definite volume. Make sense? Gas doesn't have a definite volume. So to define the volume of the gas, so we need to define how much gas I have. 1 gram, I have 1 gram, and what is the temperature, at what temperature I am storing, and what is the pressure in that bottle, something like this. So you have the mass, temperature of the gas, and pressure of the gas. If you have these 3 things, and you only can say, oh, I have that much, this much volume. Otherwise, without knowing mass of the gas, temperature of the gas, and pressure of the gas, I cannot say what is the volume of the gas. Yeah. So we will do those kind of thing in laboratory, in lab 2 and lab 3. Make sense? So gas doesn't have a definite volume. So kinetic energy means thermal energy. I already talked about that. Kinetic energy is the motion. Yeah. So so in solid, the particles are not moving fast. So lowest kinetic energy. In liquid, the particles are moving a little bit faster, a little bit higher kinetic energy. In gas, the molecules are rapidly moving, so they have highest kinetic energy, and thermal energy is same. Everybody got that? Good. So now let's talk about the mixer. I already told what mixer is. Mixer meaning that you take 2 or 3 things and you can dump how much you want to dump together, right? So that's a mixer. So mixer. So mixer means mixing 2 or more things. Mixing 2 or more things in any ratio we like. More things in any ratio. Any ratio. You can take 1 kg salt and 2 kg water, and you can dump together, right? Or you can take 5 kg water and 1 kg salt, and you can dump together. So that they are called mixer, right? So in any ratio. Now, mixer are 2 kinds. One is a homogeneous mixer. Mixer. Another is heterogeneous mixer. So heterogeneous mixer. So homogeneous mixer meaning that it's a uniform. So everywhere is same. So you look. So for example, you take water here in the beaker and put let's say 2 spoons of salt here, right? 2 spoons of salt here, right? So you are seeing here water here. Water is a liquid phase here. This is a salt is a solid phase here. So you are clearly seeing 2 phase here. So this is a heterogeneous mixture. Everybody got that? Because you are seeing solid phase and liquid phase separately. Make sense? So 2 phase or 3 phase, if you are seeing that kind of mixture is called a heterogeneous mixture. Now, still with the spoon, and all the salt particles are gone, and everywhere the solution looks the same, only 1 phase, right? It only looks like the liquid. Make sense? So that is the homogeneous mixture. Next, homogeneous means same, heterogeneous meaning different. Make sense? So, like that. So take some water here and put some sand here. So sand particle. So sand is a solid, and then water is liquid. So you are clearly seeing the 2 phase, liquid phase and solid phase. So this is a heterogeneous mixture. If there are 2 or more phases in the mixer, they are called the heterogeneous mixer. And then, but if in the mixer there is only 1 phase, that is called the homogeneous mixture. Make sense? So how about this one? So let's say you have some copper piece. So you have some copper piece here, COPPR, copper piece here, and you mix with some gold piece. So these are gold piece. These are gold piece. So all are in the solid phase. Is this a heterogeneous mixture or homogeneous mixture? It's a heterogeneous mixture because you can clearly, although this is in the same phase, but you can clearly see with your eyes that, okay, I can see clear, some gold and some copper separately, right? So this is a, although this is a solid phase, all are in the, looks to be in the same phase, but you can clearly see the difference between gold and copper. So that's a heterogeneous mixture. Make sense? But probably you could just put gold and copper in a very high temperature furnace and melt them and mix together, and maybe they mix very well, and you cannot identify where is the gold and where is the copper, and that in that condition, that solid becomes the homogeneous mixture. Everybody got that? So basically, you should not be able to see two things there to be homogeneous. Yeah, good. So like that. So for example, sand and water is heterogeneous mixture. Salt dissolved in water is a homogeneous mixture. And there is another kind of the famous mixture. So this is a beaker. We have water here. This is water. Now dump some cooking oil or something here, and this is the water here. And if you put water, the oil in this liquid phase, the oil just float here like this. Yeah. So if you go home and just take some water and put some cooking oil in the water and try to shake it, you never be able to mix them well. You always see two phases separating from one another. You clearly see, oh, there is up there is the oil, down there is a water, right? So this is heterogeneous because you are seeing two phases clearly. And though if you see the solid liquid term here, so this is also liquid phase. This is also liquid phase. This is also liquid phase. Or you might say, oh, they both are in the liquid phase, so maybe it's a homogeneous. So that I'm not saying that, yeah. So I'm saying you need to be able to see difference there with eyes. Make sense? So this is what they don't say this is liquid phase. So since this is also liquid, this is also liquid. So what scientists say is that okay, this is an oil phase, and this is a aqueous phase. Aqueous, AQUEOUS, aqueous phase. Aqueous phase means water, oil or organic phase. Sometimes they call organic for the oil. So like that. Everybody got that? So see, if you write the phase, liquid, oh, that's a liquid phase, that's a liquid phase. Maybe liquid, by using word is homogeneous, right? But it's not homogeneous because you see the oil floating in the water. So they say, okay, this is the aqueous phase, this is the oil phase. So this is a heterogeneous mixture. Everybody got that? Yeah, good. So now pure substance. So pure substance. So pure substance. So these things looks very simple, but in chemistry, these things are really, really important. Yeah, because oil. So all chemists are doing every day. They go to the lab and they are working with the oil and water mixing. I mean, organic compound and mixing with the water, and then they are separating and doing some experiments. Yeah. So like this. So pure substance. So what is pure substance? So pure substance. I'm in the slide number 8. So pure substance are. Oh no, I'm in the slide 7. Pure substance. So pure substance means. How do you know if water is pure or not? So I say, oh, I'm drinking a very pure water. How do we know if water is pure or not? So one thing, yesterday we talked, and pure water has the density of 1 gram per cubic centimeter, right? So if you take the 1 milliliter water or 1 cubic centimeter water and put in the balance, its mass is always 1 gram. Yeah. So it's a very unique property, right? So the density of water is 1 gram. So there is nothing in the universe that has exactly 1 gram per cubic centimeter density. So if that's a 1 gram per cubic centimeter you measure the density of something and you found 1 gram per cubic centimeter. Oh, then you think that probably this is water. Yeah, make sense? So another one is I can do another experiment. So if I have water and I have this water here and I want to measure is this water pure or not? So I want to find, right? Now I put thermometer here and I put it in heater. I put it in heater and I keep heating, and the thermometer temperature is 200 degrees centigrade, and the temperature never go above 100 degrees centigrade. The water boils and boils and boils, and the temperature of water always 100 degrees centigrade unless all water is gone. Make sense? So water has a 100 degrees centigrade boiling point at certain conditions. Make sense? So the pure substance has very unique property, like its boiling point, the melting point, the density. So this kind of property are very unique to the pure substance. So if this, I see 100 degrees centigrade all the time in my experiment, this is definitely water. Yeah. But if I am seeing this as a, let's say, maybe 96 degrees centigrade, this is not water. Maybe somebody mixed alcohol here or something is there. Make sense? Or if I'm seeing 110 degrees centigrade while this water is boiling, I'm seeing all the time 110 degrees centigrade, probably somebody put salt here, something like that. If you put the salt, water boils at higher temperature. So it doesn't boil at 100 degrees centigrade. Make sense? So the impure substance, the pure substance has a unique defined property. So if something boils at 100 degrees centigrade, meaning that is definitely pure water. Good. So like this, a pure substance has well-defined physical and chemical properties. So I just say a well-defined physical property of water is the boiling point of water is 100 degrees centigrade. 100 degrees centigrade. Well-defined physical property, right? Or if I freeze this water, I will see around 0 degrees centigrade, everything becomes ice. Yeah. But if there is some salt here, the temperature of this ice goes below 0 or maybe minus 0.5 or something like that. So this is not the pure water. Everybody got that? So it means that a pure substance is that substance that has very well-defined physical and chemical properties. Yeah, good. So I'm not talking chemical property here. So pure water freezes at 0 degrees centigrade. So put the thermometer, put your water in freeze and put thermometer and see at what temperature it becomes ice, and look, the thermometer is always showing 0 degrees centigrade there. And then boil it, put thermometer and water is boiling, and always you will see 100 degrees centigrade in that thermometer. Yeah, so that means that they have very well defined physical property there. So that's pure substance. So pure substance are two types. One is so this is a physical characteristics. We don't do that many physical characteristics in laboratory. We will be doing a lot of chemical characteristics. Yeah. So in laboratory, we'll measure some density or some basic thing, but most of the thing in laboratory will be doing the chemical stuff. Yeah, chemical characteristics. Now, pure substance can be classified into two kinds. So the one is the element, and another is compound. So pure substance are two types. So element. So look at the periodic table. So iron. So iron, Fe. So this is a pure substance, right? Now melt the iron. So iron has a certain melting point. If that, take a solid and try to melt this, and if that substance melts at a certain temperature, record that temperature and compare with the known value, and the iron will be, if that melt at that temperature, that is definitely a iron. Yeah. So all these data. So what is the melting point of iron? What is the melting point of pure copper? What is the melting point of all these elements? So at what temperature they become gas? What temperature they boil? So people have done all experiment and put all data in the book. So you just do your experiment and you will find something from your experiment and take that book and compare with those data, and you can easily see whether this is pure or not. Make sense? Like that. So meaning that, so somebody give me a piece of iron and I want to find is this iron or not iron. So I'm going to melt it. So I put a thermometer in the oven and I put my thermometer here and I will melt it here. So let's say this melt at 600 degrees centigrade. That's my my experiment, right? Now I go and find that book people have done, and they have a lot of data here. Okay, iron, copper, so they have many data. So maybe they say 700 degrees centigrade. So they say, okay, pure iron melt at 700 degrees centigrade, right? So when I compare this with this one, my iron melt at 600, but pure iron should melt at 700. So I should believe this data. So my iron is not pure. Make sense? Everybody got that? That's how we compare. So this is the standard value. This is our experimental value. So yesterday we talked about those things, right? Like the precision, those kind of things. And how about the, so this is the, so this element cannot be converted into other elements. So this is, what is element? Element cannot be further simplified into other elements. So iron cannot be cut into smaller pieces, and we cannot make iron into hydrogen, right? It cannot, element is very tiny unit of the material that cannot be further cut into other elements. Make sense? So I cannot cut iron and make hydrogen. Make sense? So if you look the iron weight, maybe the weight of the iron is 56. So 56. So 56. The weight of hydrogen is 1. So you might think that, okay, the 56 can be cut into 56 pieces, and one of the pieces could be hydrogen. We cannot do that, right? So long time ago, when we didn't have this kind of chemistry, they call alchemy or something like that. They would try something like that. So they would try to cut iron and into small pieces and try to make hydrogen. Or they would try to combine copper with something and try to make the gold, something like that. But the chemistry doesn't work that way. That's alchemy. Yeah. So element cannot be cut further into other simpler element. No matter how many pieces you cut, it still is iron. Everybody got that? Good. So how about the compound? What is compound? So compound is when two elements combine. So this is a hydrogen. So this is one hydrogen. This is oxygen. So if I combine this guy and this guy together, I need to combine them in certain ratio. So look here, 2 hydrogen are combining with 1 oxygen. We don't write 1. So 2 hydrogen are combined with one oxygen. So if 2 or more elements combined in certain specific ratio. If you take the ratio here, there is hydrogen, there is oxygen. So how many hydrogen? 2. 2 hydrogen are combining with how many oxygen? 1 oxygen. 2 by 1 ratio, right? Hydrogen. So if that is the case, they are called the compound. Make sense? If 2 or more elements chemically combine in certain fixed ratio, the fixed ratio, not never like H3O is another thing. It's not a water. Yeah, it's not a water. So something else. This is an acid, but only this is a water. Make sense? So there is I have 3:1. Here I have 2:1. So this is water compound. This is something else. This is not water. Everybody got that? So the 2 elements must combine in certain specific ratio. That's called compound. So we are just moving fast here. So, all right, now another thing here, I am now in slide number 9. So let's see here. There are, when we do the experiment in laboratory, we need to make the observation, right? So what kind of the observation we are making? So you go to the laboratory and you do something and somebody asks you, what kind of observation you make? And you could not answer, right? So that's bad, right? So therefore we need to identify this terms. So there are 2 kinds of the observation we make when we start to do the experiment in the laboratory. Yeah. So one is quantitative observation. Quantitative observation. Observation means we are looking something quantitatively. Quantitative means how much. Quantitative means how much. You are basically answering how much or how many. How many. So you are just looking the answer for in quantitative observation, or how much material you measure, or how many moles of material were there. Yeah, something like that. You are looking the how many or how much of the material, and that kind of the observation we are making is called quantitative observation. Make sense? So, for example, let's say you have some salt here, sodium chloride. Sodium chloride is a very simple salt that we eat every day in our kitchen, right? So like this, and now your job is to measure some, let's say 2.0 gram of sodium chloride in laboratory and do the experiment, right? First of all, now you go to the balance. You go to the balance here. So balance has a reading pan here. You put a weighing board here, and you make 0, and take like a couple of spoon here and put the salt here. Okay, so you are trying to measure 2 gram here, but you make, let's say 2.1 to 3 gram of the salt you could measure here. So what kind of observation you make now? That's a quantitative observation you make. Make sense? So if you are looking the measurement and giving the number and unit, that kind of the measurement, that kind of observation is called quantitative observation. Everyone got that? So this is a number, this is a unit. So this gram is a unit, this is a number, right? So you did some experiment and you found a number and you give the unit. So number comes with the unit, and this kind of work or this kind of observation is called quantitative observation. We have all done this, right? But we are just studying here systematically. Everyone got that? So for example, what is my height? So I take the scale and I measure my height, and I am 5 feet 4 inch. 5 feet 4 inch. So if you see here, so the number and unit, So I am doing the quantitative observation. Everybody got that? Right. Good. Anything you measure, you weight, length, breadth, volume, whatever you are measuring and giving number and the unit, and that kind of observation is quantitative observation. Now, how about the qualitative observation? Now, again, from the word, you can easily know this one, qualitative observation. So basically, qualitative observation is, how does it look like? How does it look like? How does it look like? You're not measuring and you are not giving numbers here. You're just trying to answer, how does it look like? What happened, right? Was it hot? Or, is it cold? You're not saying, okay, my water is 25 degrees centigrade. If you write this one, this is not the qualitative. This is a quantitative, because you are giving the number and you are giving the unit, right? So that becomes a quantitative, number with the unit. But somebody asked, how does the water look like? Oh, it was warm, right? It was warm. I can drink. So warm. So warm is qualitative. We are just talking about some quality of water. No number. Yeah. Everybody got that? Right. So or let's say here is a yellow solution. So here is yellow solution here. Maybe here is a black solution of something, and let's say here is a blue solution of something. Now you mix these two together, and maybe when you mix this together, you got let's say some purple solution or purple precipitate or purple solution. You see that? So this is a qualitative observation. Maybe make sense? So I have some solution of a substance that's black. I have solution of another substance that's blue. Now I just put this blue to the a black solution, and when I mix these two together, and new solution appear to be pink, right? So I didn't give any number or unit here. So I just see how it looks like, right? So that's a qualitative observation. Everybody got that? Sometimes not only color. Sometimes what happens is that you will see some solid. Solid is coming here. Solid comes here like this. So you mix this clear solution, liquid, and two liquid you mix together, and new solid form here. And you say, oh, okay, I got a precipitation, like the water, the vapor is raining down, right? So precipitation, they call precipitation. So I mix solution A, that was black, solution B, that was blue, and when I mix these two together, I got some solid that looks like the pink. So we call precipitation. So this kind of the thing are called the qualitative observation. Everybody got that? Number and unit. If you are looking trying to give number in unit, quantitative observation in anything. But if you are just looking with the eyes, that's a qualitative observation. Good. All right. So like this one now. Okay, we have still some time. So now. So next week, when you go to the laboratory and you will be measuring some water, and the lab manual say, okay, measure 20, put water, approximately 20.0 ml of water in a graduated cylinder. So you are going to put, so this is your, this one, cylinder, and you are going to put approximately 20 ml of water up to here. So this you are doing is a quantitative observation. Make sense? Good. So now let's look chemical and physical change. So if you look your textbook, and at the end of the first chapter, you will see a lot of this kind of question. Yeah. So like, my water is warm. Is that a qualitative or quantitative? Or I say my water is 25 degrees centigrade. Is that a qualitative or quantitative? So there are a lot of those kind of questions. Yeah. So you see, when you see the number and the unit, immediately quantitative. Good. All right. So now let's look at chemical and physical change. So chemical and physical change. Physical change. So what is the chemical and physical change? So now I'm in slide number 10. Now. So chemical change and physical change. So in physical change, so it looks different when we look with our eyes, but essentially its composition is the same. So that kind of change is called physical change. Yeah. So for example, you have water here. You have water here. So this is liquid water, liquid water. Now you put in the freeze and it becomes solid. It becomes solid. It's ice, and now you heat, and you have to heat it further, and it becomes vapor. Like this becomes vapor. Look here. So when you look with your eyes, or you try to touch these things, they feel different, right? They look different, or they feel different. But you do the chemical analysis. So this guy, the liquid is H2O. Put this thing in some instrument, and that instrument tell, oh, there is only H2O. That tells that, yeah. So at this point, you don't know how do I know is it S2 or not, but there is a way to find whether it's S2 or not. So put this ice and throw in that same machine. That machine say, oh, there is only H2O. Yeah, and then throw this vapor into that machine, and this or that machine now also say that H2O, right? So in all cases, you see the change. You change the liquid to solid, to this ice, to then it changes to vapor. It looks like you are changing, right? But essentially, the chemical composition of the material is not changing. It's the same thing. Make sense? So this kind of change is called physical change. No new substance is formed. So water, ice, and vapor are the same thing. Make sense? So no new substance. Ice is not a new substance, or vapor is not a new substance. Liquid is not a new substance. All is the same. So liquid, solid, or vapor of the water is essentially all is H2O, H2O, H2O. So no new substance is formed. Can I convert liquid to ice easily? I put in the freeze and liquid goes to ice, right? And I take the ice out of the freeze, easily it goes back to the liquid, right? It's a reversible. So physical change is reversible. Reversible meaning that it can be changed one way, and that material can easily be changed to the other way. Or I have vapor. I have vapor here. Can I convert vapor to ice easily? So I take the vapor in a container, and I put in the refrigerator, and the vapor becomes liquid, and liquid becomes ice. So easily they are reversible. Physical changes are reversible. No new substance is formed in this change, and the change is reversible. Good. So how about this one? So that's a I just give the example of the ice here. Now let's melt the iron. So I have a piece of iron here. So this is iron. Now if I heat it very high temperature, this iron becomes liquid. Liquid iron. Right? Liquid iron. So this is also, if you look the, take this small piece of this and throw into the machine, it will say, oh, there is Fe. And then take a little bit of this and throw into the machine, it says Fe. So essentially, this is the same material, right? Make sense? Now, if you heat it, if you heat the solid iron, it becomes the liquid iron. Now, cool this liquid iron, and it becomes the solid iron. Now, this is also reversible. Make sense? It's the same thing. So when we look with our eyes, it looks the change. It looks like there is a change, right? But it's really not the change. It's a reversible. It's a reversible. It can be reversed back. Now, chemical change. So we're almost there. So chemical change. Now it's the opposite of the physical change. So chemical change is new substance is formed, completely new substance is formed, and not reversible. You cannot convert back. Not reversible. Not reversible. So, for example, I have a example here. So you have a wood here. So this is a wood piece. W-O-O-D, wood. Make sense? So wood. Wood is basically this kind of compound. C6H12O6, cellulose, glucose. This kind of compound is the wood. Make sense? Now, if you burn the wood, burn it. B-U-R-N. Burn it, and you get all coal. You get coal. Coal is only carbon. Carbon. Can you convert coal to wood? Impossible, right? So, or the firewood, right? Firewood. You go to the quick tree, buy a firewood, take home and burn it, and you get all coal here. Now, the wood was something like this. Now you get the coal. Can you convert coal to the wood? Impossible, right? So this is this kind of change is called chemical change. Make sense? So completely new substance is formed here. This is C. This is C6H12O6, and not reversible. I cannot change coal to wood. Yeah. Or like the yogurt, right? So you have a milk and you put some bacteria, milk changes to yogurt. Can you convert yogurt to milk? Impossible, right? So this kind of change are called chemical change. Good. Like that. So completely new substance is formed. So I have 4 minutes left. What I have here. So let's see. So thermal energy in different state. I already talked this thermal energy in different state concept. So I just repeat it here. So thermal energy meaning that particles are moving. If the particles are moving, they have higher thermal energy. Make sense? If they are moving slowly, they have less thermal energy. So for example, this is ice. Ice particles are not moving that fast, so they are cold. So thermal energy is not high. They are not that warm, right? But if you give some heat here, so this is water. So if you put your hand here, it's a warm. It's more thermal energy. Thermal means it's a heat. Makes sense? Hot, warm. So less thermal energy in solid, more thermal energy in liquid. So the particles here are tightly bound. They are not moving each other that fast. So cold here, move a little bit faster, more warm and more thermal energy. And when you have a gas, they are more hot and the particles are moving much faster, more thermal energy. Yeah. So higher the temperature, higher is the thermal energy. So for example, so I'm comparing here solid, liquid, and gas, right? So gas has highest thermal energy, liquid has a little bit lower thermal energy, solid has the lowest thermal energy. Make sense? So how about the same temperature, same state, different temperature? So let's look here. So you have water that we drink in our everyday life has a 25 degrees centigrade. So you go to home and you take some water from a tap and measure the temperature 25 degrees centigrade. Now heat it. So put it in the heater, and this will absorb some thermometer. So some heat is absorbed, and it shows 50 degrees centigrade. Now it's also water. It's also water, liquid. So which has a more thermal energy? This guy, because higher temperature meaning that the molecules are moving more faster. Everybody got that? So if you are looking the liquid state or gas state, whichever has a higher temperature, that the molecules are moving faster, meaning that has higher thermal energy. Everybody got that? So thank you, everyone. So we will start next chapter in next class.